I want to show you a question from a university linear algebra course. It asks you to prove something about eigenvalues and eigenvectors, and if those words mean nothing to you right now, that is exactly where I want you. By the end of this video, you will answer this question yourself on paper with almost no calculation, because you will understand what every symbol in it actually says. We are starting from nothing. Not from Chapter 1 of a textbook, from before Chapter 1. Here is the first thing you need, and I mean the very first. A vector, for everything we do today, is an arrow. It starts at one fixed home point, which we call the origin, and it points somewhere. Two things describe it completely: how long it is, and which direction it points. That is all a vector is. An arrow with a length and a direction, anchored at the origin. And the word itself tells you this. Vector is Latin for carrier, the arrow that carries you from the origin to a point. Now, the one operation you must feel in your hands, multiplying a vector by an ordinary number. Multiply the arrow by 2 and it doubles in length. Same direction, same line. Multiply by 1/2 and it shrinks. Same direction, same line. Multiply by a negative number and it flips to point the opposite way. But look carefully, it is still lying on the same straight line through the origin. A number can stretch, shrink, flip, or collapse an arrow to the origin. Mathematicians call such a plane number a scalar, from the Latin scala, a ladder, because all it can ever do is scale things up and down. So when a question says C and D are scalars, it means exactly this: ordinary numbers. A number can never turn an arrow off its line. So every arrow owns a private straight line, the line through the origin in its direction. Your textbook has a name for this private line: the span of the arrow, everything you can reach by scaling it. Every number you multiply by keeps the arrow somewhere on that private line. Hold on to that picture, the arrow and its own line, because the entire video and the entire question we are chasing lives on that line. Now the second character, the matrix. Forget the grid of numbers for a moment. A matrix is a machine. You feed it an arrow and it hands you back a new arrow. One machine, applied to the whole plane at once, moves every arrow simultaneously. It stretches space, squeezes it, shears it, rotates it. When I write the letter T today, I mean that machine. The grid of numbers itself is called a matrix, Latin for womb, because the entire machine is born from those few numbers. Feeding the arrow V into T is written as T applied to V, and the output is itself a new arrow. Matrix machines are not arbitrary. They obey two house rules, and you can see both. Rule 1. If you add two arrows and then feed the sum into the machine, you get the same result as feeding each arrow in separately and adding the two outputs. Rule 2. If you scale an arrow by a number first and then feed it in, you get the same result as feeding it in first and scaling the output by that number. These two rules are what the word linear means, and they are why the machine moves space smoothly. Grid lines stay straight, the origin stays home. A machine obeying these rules is called a linear map, linear from the Latin for line, and when it sends a space into itself, your book calls it an operator. Those are the names you will read, so from here on, so will I. Let me now hand you one specific operator, and we will use this exact operator for the rest of the video. Watch what T does to an ordinary arrow, the arrow pointing to the point 1, 1. T sends it to the point 4, 2. Now check the picture. the output is not on the input's private line. The operator did not just stretch this arrow, it turned it. And for a typical matrix, this is the fate of almost every arrow you feed in, stretched and turned. But now, feed the same operator a different arrow, the arrow pointing to 1, 0, straight along the horizontal. The output is the arrow to 3, 0. Stop. Look at where it landed. It is on the same line, same direction, 3 times the length. The operator, which turns almost everything, could not turn this arrow. For this particular direction, the whole complicated operator collapsed into something you already understand completely: multiplication by the ordinary number 3. Get your pen. This is the first thing you will write today, and it is the sentence the entire subject is built on. Write this exactly. T applied to V equals lambda times V. Now let me tell you what you just wrote, symbol by symbol. T is the operator. V is one specific non-zero arrow. Lambda is one ordinary number, a scalar, written with the Greek letter mathematicians reserve for eigenvalues. And the equal sign is the miracle. It says that feeding this arrow through the entire operator gives the exact same result as multiplying the arrow by one plain number, which, as you saw, can stretch, shrink, or flip the arrow, but can never turn it off its own line. These objects have names, and here are their official definitions. Write both down. First, a number lambda is called an eigenvalue of t if there exists at least one non-zero arrow v with t applied to v equal to lambda times v. Second, any such non-zero arrow v is called an eigenvector of t corresponding to lambda. The German word eigen means own, as in one's own, an intrinsic possession. The eigenvalue is the operator's own number. The eigenvector is the direction the operator owns without turning. In our running example, 3 is an eigenvalue of our operator, and the arrow to 1, 0 is an eigenvector for it. One clause in those definitions is doing quiet, essential work. The arrow must not be the 0 arrow, the arrow of length 0 that goes nowhere. Here is why. Feed the 0 arrow into any operator whatsoever. Out comes the 0 arrow. And the 0 arrow times any number is also the 0 arrow. So the 0 arrow satisfies our equation for every operator and every number at once. It would make every number an eigenvalue of everything, and the definition would tell us nothing. We ban the 0 arrow so that an eigenvalue remains a rare, meaningful property of the operator. Now we verify an eigenvector by hand, and you write every line with me. Claim: the arrow to 1, negative 1 is also an eigenvector of our operator. Write line 1. T applied to the arrow 1, negative 1. Compute it with me. Top entry, 3 times 1 plus 1 times negative 1, which is 2. Bottom entry, 0 times 1 plus 2 times negative 1, which is negative 2. Write line 2. The result is the arrow 2, negative 2. Write line 3. The arrow 2, negative 2 equals 2 times the arrow 1, negative 1. Read what your own 3 lines just proved. T sent this arrow to twice itself, no turn, so 1, negative 1 is an eigenvector, and 2 is a second eigenvalue of the very same operator. Before you believe every operator owns such directions, watch one that owns none. The operator that rotates every arrow by a quarter turn. Feed it any non-zero arrow at all. The output is turned 90 degrees. and an arrow turned by 90 degrees can never lie on its own line. So this rotation operator has no eigenvector and no eigenvalue among the real numbers. An eigenvalue is not a guarantee. It is a discovery about a particular operator, which is exactly why you are asked to prove things about them. After the break. Welcome back. 2 more tools and we open the question. Tool 1, the identity matrix, written with the letter I. It is the operator that does nothing. Feed in any arrow, and the output is the same arrow untouched. Its name is honest, identity, from the Latin idem, the same, because what comes out is identical to what went in. It sounds useless, and it is precisely its uselessness that makes it powerful. It is the operator version of the number 1, the do-nothing element we can mix into other operators on purpose. Tool 2. Building a new operator from an old one. And this is the exact object the question is about. Write its meaning down. Take our operator t, a number c, and a number d. The new operator, written c times t plus d times I, acts on an arrow v in 3 steps. Step 1. Feed v through t and scale that output by c. Step 2. Feed v through I, which returns v itself, and scale it by d. Step 3. Add the 2 resulting arrows tip to tail. Write this as one line. ct plus di applied to v equals c times t applied to v plus d times v. That line is not a theorem. It is the definition of what the new operator means, and it is the only key the question needs. Now the question comes back to center stage, and this time you can read it. It says, T is a matrix, an operator. Lambda is one of its eigenvalues, V a corresponding eigenvector. So we are handed, for free, one non-zero arrow that T merely stretches by lambda. C and D are ordinary numbers. Part 1 asks, show that this same arrow, V, is also an eigenvector of the composite operator Ct plus Di. Part 2 asks, if T is diagonalizable, a word we will define completely when we reach it, show the composite operator is diagonalizable too. Before any writing, understand what is truly being claimed in pictures. We know T cannot turn the arrow V. It only stretches it by lambda. The claim is that the new composite operator, built by scaling and mixing, also cannot turn V. Same untouchable direction. Only the stretch factor is allowed to change. And to prove someone's arrow is an eigenvector, the definitions you wrote tell you exactly what must be shown. The arrow is non-zero, and the operator's output on it equals some single number times the arrow. That is the whole job. Pen ready. The proof is 4 written lines, and you will understand each one before the next exists. Line 1. Write the given facts. T applied to V equals lambda times V, and V is not the zero arrow. This line is your inventory. It is everything the question handed you stated in symbols, and a proof may only spend what is in its inventory. Nothing else is known, nothing else will be needed. Line 2, write Ct plus Di applied to V equals C times T applied to V plus D times V. Why are you allowed to write this? Not because of algebra you memorized, because of what the composite operator means. You defined it yourself 2 minutes ago. feed v to both parts, scale each output, add. This line is that definition, applied to our specific arrow. Every equal sign in a proof must have a reason, and this one's reason is definition of the operator ct plus di. Line 3, write, this equals c times lambda times v plus d times v. The reason for this equal sign sits in line 1. Line 1 told us the operator's output on v is lambda times v, so wherever the expression t applied to v appears, we may replace it with lambda times v because they are the same arrow. Notice what just happened on your page. The operator t is gone. From this line onward, there are no operators left in the expression, only numbers multiplying one arrow. Line 4, write, this equals the quantity c lambda plus d times v. The reason? C lambda times v plus d times v means stretch the arrow by c lambda, stretch the same arrow by d, add. And stretching one arrow twice and adding is one stretch by the combined amount. Two scalings of the same arrow collapse into one number. Now write the conclusion sentence. Since v is non-zero and the composite operator's output on v equals the single number c lambda plus d times v, the arrow v is an eigenvector of ct plus di with eigenvalue c lambda plus d. Check your checklist. Non-zero, given. Single number times v. The number is c lambda plus d, sitting on your page. Part 1 is fully proved. Proofs earn trust. Numbers make it visceral. Watch the claim happen. Take our operator. Take c equal to 2 and d equal to 5, and build the composite operator 2t plus 5i as an honest array of numbers. Work it out, and its top row is 11 and 2, its bottom row 0 and 9. Feed it our first eigenvector, the arrow 1, 0. The output is the arrow 11, 0, 11 times the input. Now compute what our theorem predicted the new eigenvalue must be, c lambda plus d, which is 2 times 3 plus 5, 11. The picture, the proof, and the arithmetic just said the same sentence in 3 languages. Sit with what Part 1 really says, because it is bigger than this one question. The operator's own directions are structural. Scale it, mix in the identity, and those directions do not move. Only the operator's own numbers respond, and they respond by the exact same recipe applied to them. Lambda becomes c lambda plus d. Knowing one eigenvector of t instantly hands you an eigenvector of an entire infinite family of operators for every choice of c and d, with every eigenvalue known. That is what a definition, properly understood, pays out. Part 2 of the question uses the word diagonalizable, and I promised we'd define it from the ground. So we need one prior idea, combining arrows to reach places. Take our 2 eigendirections, the horizontal arrow 1, 0, and the diagonal arrow 1, negative 1. A combination means scale the first by some number, scale the second by some number, add them tip to tail. The full name in your book is a linear combination. Scaling and adding, the only 2 moves a linear world allows. Watch. By choosing the 2 scaling numbers, the combined arrow can be made to land on any point of the plane whatsoever. 2 well-chosen arrows are enough to reach everything. A set of arrows with that property has a name. Write the definition. A basis of the plane is a set of arrows such that every arrow in the plane can be produced as a combination of them, and none of them is wasted. No arrow in the set is itself a combination of the others. The 2 clauses have official names you must recognize. Reaching everything is called spanning, and wasting nothing is called being linearly independent. Basis itself is Greek for foundation, the arrows everything else stands on. For n-dimensional space, the same idea needs n arrows. A basis is a complete, non-redundant set of building directions. Once you have one, every arrow in existence is expressible through it. Now the question's word, defined completely. Write it. An operator T is called diagonalizable if there exists a basis made entirely of eigenvectors of T. Feel what that buys you. In such a basis, every building direction is a direction the operator cannot turn. So the operator's entire action is just stretch the first basis direction by its own number, the second by its own number, and so on. Written as an array in that basis, the operator has its eigenvalues down the diagonal and zeros everywhere else, which is where the name comes from. Diagonal is Greek too. Dia, across, gonia, angle, the line running corner to corner. Our running operator qualifies. The 2 eigenvectors we found form a basis of the plane, as you watched them do. Part 2 now proves itself in 3 written lines. Pen ready. Line 1. Suppose T is diagonalizable, so there exists a basis of arrows, each one an eigenvector of T with its own eigenvalue. Line 2. By part 1, applied to each basis arrow separately, every one of those arrows is also an eigenvector of the composite operator, with its own eigenvalue transformed by the recipe C times it plus D. Line 3. The conclusion. The very same set of arrows is therefore a basis consisting entirely of eigenvectors of C, T plus D, I. And that is, word for word, the definition of the composite operator being diagonalizable. Notice you performed no new computation. Part 1 did all the labor. Part 2 is Part 1 applied to each basis direction, plus the definition read honestly. One closing observation that opens the next door. The composite operator, Ct plus Di, is a polynomial in T of degree at most 1, T treated like a variable, scaled and shifted. And its eigenvalue came out as the same polynomial evaluated at lambda. That pattern runs deeper than degree 1, and it becomes a central tool of this entire subject. But it also sharpens the question we quietly stepped around all video. We verified eigenvalues we were handed. How do you find them when nobody hands them to you? That search has a name, the characteristic equation, and it is exactly where we go next. Look back at your page. You defined an arrow, an operator, and the one equation that says an operator sometimes behaves as a mere number. From those definitions alone, no determinants, no formulas, you proved a university question in 7 written lines and a conclusion, and every equal sign on your page has a reason you can state out loud. That is what this subject actually is underneath the notation, and it is yours now. Next time, we hunt eigenvalues from scratch. I will see you there.